Okay. Okay, so good afternoon. So welcome to the afternoon session, and our first speaker is Supriya Krishnamurthy from Department of Physics, Stockholm University, and she's going to talk about thermodynamic uncertainty relations. Supriya.
Thank you, Satya. I guess you can all hear me. The mic is okay. A bit louder? Okay. Yes, so it's a very, very great pleasure to be here on this very happy occasion. Congratulations to Deepak. And to see many of you who I haven't seen for far too long, really, 20 years, I think. So thank you very much to the organizers and to the ICTS supporting staff for getting all this in shape. So today I'll talk about these things, this set of relations, or as Deepak pointed out, inequalities, which are rather of interest nowadays. So there's a lot of work being done on that. But I'll talk about this in a very sort of basic kind of introductory level. I apologize in advance to the experts, but I hope that some of the younger people who haven't seen it will get something out of the talk. So I myself am no expert, and all I learned from basically when Shrikant was doing his PhD with me. He finished in 2020, and he's now a postdoc in Stanford. We also are, another collaboration has also been with Deepak Gupta, who maybe many of you know, Sanjib's student, and he's currently in Berlin. And I also have other collaborators. So Shun was a PhD student with Takahiro, and then Oyon Banerjee's group, Bishwajit is here, and Dhruba, also who many of you know. Lots of people, but not lots of papers. Okay, but actually, that's normal, right? Yeah. Okay, so I actually won't talk about my work very much. I will just get to it in the end if I have the time. And I will not take more time because Deepak's coming next, so I won't dare to take more time. So whatever I manage to finish, I finish, and if I don't manage, I don't manage. That's how we do it. So, okay, so these thermodynamic, and the plan of the talk is that I'll just talk about these thermodynamic uncertainty relations. So that's it. So it's this relation, or this inequality. Okay, so and we are going to try to understand this and try to see, okay, why is it interesting? So this fancy J is a kind of current in your system. Remember, so we are talking of non-equilibrium steady states. Now it turns out that there are variations of this also if they are not in steady states, but I won't talk about those. So we're talking of non-equilibrium steady states. Non-equilibrium steady states have currents. That thing is a kind of current. So there's this also notion of generalized currents, which I will mention briefly. So the variance of a current upon the mean square. Okay, so that part is just here. Then there is a sigma, which is the entropy production rate. Okay, so then I'll need to explain to you where does that come into the picture. So we'll do that. Tau is the time over which you're observing your, or rather time over which you're making these calculations of variances. So imagine that you are observing your system over a very, very long time, your steady state system. But over periods of tau, you're making an estimate of the variance and the mean. It turns out for the mean, it doesn't matter how much tau is, but for the variance, it's going to make a difference, what tau is. Okay? So we can think of long, very, very large tau. We can think of very, very short tau or something in between. Okay. And then that's greater than 2. Okay, so there's actually a KB, but we are in units of this Boltzmann constant equal. And here's a nice picture taken from the PhD thesis of Patrick, who was Udo Seifert's PhD student. And here is so this was just to sort of indicate what this thing is about. Here is a, whatever it's called, a microtubule. And then there is a motor protein walking on it. Think of it like an asymmetric random walk. Okay, and then, so the way the illustration is, you start it off somewhere. And then you observe it over a period tau. And in that period, it has managed to go some distance. So this distance you can think of as a kind of current in the system. And I think the color coding here is that, if it's brighter, then it's more likely it's ended there. In many, many realizations of the process, that motor protein ended there or there or there, and sometimes it ended there, sometimes it ended there. So you can talk of a mean, you can talk of a variance. And then this thermodynamic uncertainty relation is trying to make a connection between the variance upon the mean square to this. So where does dissipation come in? So something clearly is making that protein move. Okay, so some change, some difference in chemical potentials, some force. Yes.
Sorry, when you in this motor protein example, are you working at non-zero number density, or is it just repeated runs with one?
Repeated runs with
one.
Yeah, for example.
I see.
Yeah.
Okay.
And we'll look at that model a bit closely, because that's often used as an example, just because it's so simple. Okay, so where does dissipation come in? Well, so something is giving that protein, ATP is burning to ADP, or whatever is making that thing walk on the microtubule. So it's using some of that. So you can make it do some force as it walks. You can make it do some, sort of a counter. You can put a counter force and it's pushing. And so some of that energy is being used by it to do the work, and some is being dissipated. So that's basically where dissipation comes in. And what this thermodynamic uncertainty relation thing is that there's some connection between this dissipation and this ratio. Okay. The time integrated current. So the current variable is a time. So these are time extensive quantities. Okay. Sigma and J will both vanish. They will vanish in a way such that we will talk briefly about that, because that's it's well studied in the linear response limit. And there actually it's understood. Okay, I might as well say it right here. There it's understood that it's an equality. So so whenever you have an inequality, then you always think, okay, is it tight? Is that bound tight? Which means that can you do something such that the equality is reached? And one knows that in the linear response regime, you can reach that. Okay, so maybe we'll talk about that a bit later. I mean, like, so for example, like maybe we, yeah, so. Yeah, what will the sigma be there then? Maybe that will be 0 too. Okay, anyway, so we'll talk about, yeah. So. Okay, yeah, okay, yeah. Okay, so that's basically what it is. Okay, so now we'll just try to walk us through this thing. And what's all this hype about? Why is it interesting? There's an incredible amount of work being done, but on what? So we'll talk a bit about all that stuff. So, but before that, I just wanted to say, so we are on the same page. The models that you consider, so the models for which that thing works, that inequality works, they have to be Markovian first. And they have to be continuous time. If it's discrete time, then that particular inequality doesn't work. Then it's something else. But people have worked on variations of it. So continuous time. And then, okay, then if you're in that framework, then you can have master equations, you can have overdamped Langevin equations, you can have underdamped Langevin equations. It turns out that it works for master equations, it works for overdamped Langevin equations. It does not work for underdamped Langevin equations. Okay, so that's why doesn't it work? Okay, it's likely that it at least one, I think, understanding of why it doesn't work there is just that I think, and it's due to Christian Weiss, among others, is that in overdamped systems, maybe it's not only the dissipation that plays a role. Maybe there are other quantities called activity or frenesy or different things which can play a role. So that's one understanding. So we are not really going to talk about these underdamped Langevin. Okay, so those two, or at least maybe, yeah, not everything. So currents, so that we are on the same page. If we have an equilibrium system here, detail balance works, no currents. If you have a non-equilibrium system here, detail balance doesn't work. The current is just this minus this. Okay, so this minus this is the current along that link. Okay, so that's currents. But then what is entropy or entropy production in this whole business? So then we have to talk a little bit about this field of stochastic thermodynamics. And there the idea is that this ratio which would have been 1 in equilibrium, is E to the entropy production along a link. Okay. So why is that something reasonable? So first of all, the whole field of stochastic thermodynamics, what they say is, okay, so that first of all, if you want the system to be non-equilibrium, if all these transitions were fueled by one reservoir, then that's not going to work. Eventually, the system is going to come into equilibrium. So it must be that you can think of these transitions as being sort of fueled or by reservoirs at different temperatures, for example. That's not the only way a system can be out of equilibrium, but that's one way. So this set of transitions happened because it was in contact, sort of locally in contact with a reservoir at some temperature beta, with inverse temperature beta 1, maybe beta 2, beta 3, or whatever. So you need at least 2 temperatures before the thing gets out of equilibrium. And so what does it mean fueled by the reservoir? So the way that I've understood it is that, okay, so imagine that this transition is happening because this system is in equilibrium with a reservoir at some temperature. Then you want to understand what's the ratio of the rates of these transitions, which maybe you don't know a priori. But all that you do know is that the reservoir's energy changed, maybe. When the system was in state B, the reservoir had some energy. And the system went to state C, the reservoir had some other energy. So there was some jump of energy. But the reservoir is in equilibrium. So that ratio, you know, is just e to the minus beta delta E. So that's why this condition which leads to this is called generalized detail balance. Okay. So a bunch of approximate, I'm not aware of approximations, but there's a sort of constraints go in such a thing. But anyway, so this is generally, this works out when you have this generalized detail balance. And then this rate WBC upon WCB gives you this beta Q. Q is the sort of heat dissipated, or so the energy that's given out or given to the reservoir, which is what we call heat. And this delta S is the system entropy, PB by PS. And the two together give you E to the total entropy of the system. So the log of this quantity is the sort of entropy created with this set of transitions. You can work out the same for this set of transitions, this set of transitions. If you add them all up, you get the total entropy created per unit time, which is then sigma. Okay, so this is entropy production per link. As I said, you can keep the total number of transitions is just this current, and this rate of total entropy production is over all links. So you basically, you keep track of how many, say, transitions happened B to C minus C to B. Okay, so that's the net number of transitions. If you, that should give you a current, and then you multiply this current by this FBC, and that gives you the sigma. So that is a sort of, and it's consistent with the understanding of sigma as sort of from a trajectory point of view as log ratio of forward to backward trajectories, etc. So that is, yes. No, it's not. So because when, so you can show that this is consistent with thinking of the entropy production, or the total entropy rather, as a log ratio of probabilities. And then you can talk of log ratio of probabilities even in, yeah. So once you have this set of constraints, or, you know, you put these sort of rules on your system, then everything is clear. And then you can go ahead and calculate for the usual thing. So you have a regular non-equilibrium system that you're always used to. You can calculate all kinds of thermodynamic properties on it from here. Okay, so there's one more point which one more point which I wanted to make before we continue with the thermodynamic uncertainty relation, and that's this idea of generalized currents. So just a current was, just this one. This entropy production or rate of entropy production, or the total entropy production, is a generalized current because it's a current with a weight factor. Okay, in principle, you could put any kind of weight factor there. Of course, you could say, why is that useful? But we'll see in a bit. So, and it also, it's and one reason why this whole subject's become very interesting, as well as this thermodynamic uncertainty relation is very interesting, is that there are more systems you don't know anything about than that you know something about it. And more systems that you can't calculate anything for than you can calculate something for. For such systems, the idea is that suppose I didn't know anything about a system. I didn't know what is this WBC or anything. I didn't know how to calculate steady state probabilities. But I was given a time series. An experimentalist gave me a time series and I was able to identify states. Okay, so then I just had this, I had a time series like this. Then I would actually just sort of clump it up into series of length tau. Okay, calculate these quantities, a current. I could multiply this current by any DBC, as I said, I call it a generalized current. Okay, do the same for all transitions. So I get a total J hat, a generalized current for my system. And what this thermodynamic uncertainty relation implies is that this, no matter what generalized current you use, it could be just from one link, it could be some combination of links, whatever. If you just add them all up, of course, it should be 0 in the steady state, but that's you can multiply it by something. So any kind of weights. If you do that, and it's a current variable, current type variable, then this is guaranteed. This relation is guaranteed. Okay, so this is rather interesting because it's saying something. Yes.
How do these survive under coarse graining?
Okay. So yes, under coarse graining. So actually, this relation still works. I think there's work done on that. Or you can show, for example, that the entropy production rate or entropy production, I mean, with coarse graining typically becomes lower than the true value, whatever the true value is. So the values get changed by coarse graining, but this typically works. Okay, so why is this interesting? So I can do this for any system for which I didn't know anything, just if I just had good data. And then what this relation is saying, if I take the sigma to this side and everything else to the other side, it's saying that it's giving me a lower bound on sigma. So it's saying that the sigma is greater than equal to something that I can calculate from data. So that's very interesting. Okay, then of course there are all kinds of issues which will arise when you have data, and that is because you may not be able to keep track of all the states. There are all those coarse graining issues. So there's all those other issues that you might have to worry about. But what this is saying is that knowing nothing about a system just from data, this gives you a lower bound. Okay, how good is that lower bound? It'll turn out that how good it is depends on what the tau is. Okay, so typically when this was studied, it was studied for large tau, but we'll see that actually it gets better and better as tau gets smaller, as you observe the system over shorter and shorter times. Okay. So if we go back to our this slide here, what's that? Maybe we can, yeah, but maybe we can get rid of. Yeah. Okay. Anyway, this part of the slide you had seen. So this uncertainty relation, the first one that I showed you is called the finite time thermodynamic uncertainty relation, because it talks about observing the system over any period tau. The first version, thank you. The first version that was introduced actually by Barato and Seifert in 2015 was at very long times tau, in which case the variance and the mean are both extensive in time. And then you have a relation between completely time intensive variables. Okay, but it was very soon noticed by Piazzonka and Gingrich et al. That this actually works for any tau, which is interesting because, I mean, experimentally, I mean, this is of course something much more relevant than this. Okay, so those are the early versions of this thermodynamic uncertainty relation, at long times and finite times. Okay. Okay, so I thought, okay, we'll take two very, very simple models. Actually, these are the models often used as examples in the literature. But it still teaches you something. Okay, so as I said, that motor protein could have been an asymmetric random walk in continuous time. For that, we know the currents. It's very simple. Average and variance go like that. Okay, a generalized current would be that, for example, I could multiply this current variable x by this log of k plus k minus, and I get something like that. Okay, so those are easy things. Oh, yes, I just wanted to mention one thing in relation with this. Oh, yeah, so as I said, entropy production is also a generalized current, and macroscopically we talk about, and what we call entropy production is an average entropy production. But here you can talk of variances, higher moments, etc. Okay, so the thermodynamic consistency argument that I talked about comes in as here. The log ratio of the rates is what's called an affinity, which can be whatever is making that motor walk on the, what is making that protein walk on the thing. It could be a difference in chemical potentials, minus F, the F force times distance, etc. So, and that's the temperature. And then the sigma tau, which is the change in the entropy of the medium, is given by this quantity. And this immediately puts a bound, you can see. And here you can very easily see that the TUR works just from some simple mathematics. It gives a bound on something called the Fano factor. Relatedly, it gives you this TUR. Okay, so of course, this is just one model, not anything in general. But nevertheless, here it's a very simple model in which you can see that it works. And this was also the example used by Barato and Seifert in their PRN. You can do a little bit more, which is maybe a bit of an overkill for this model, but it sort of is important when you think of more complicated models. You can define a generating function of that sort, as of course people know how to do from very long back. Here it's very easy to calculate. And then if you weight the current appropriately, the ratio, the first and second moments immediately give you either the mean entropy production or the variance, etc. Okay. And you can see that this generating function actually is bounded by a parabolic bound for any value of A. Okay, this is very easy to see in this context, but actually this turns out to be a very general result. So the whole proof of this thermodynamic uncertainty relation was actually showing that for a generic Markov process, the generating function is bounded by this parabolic bound. Okay, for no matter how far you are from an equilibrium. Remember that the larger the A, the further you are from equilibrium. If you make A very small, that's linear response regime, then you can actually see that the equality holds. You get back sigma Z1 plus Z from this. But it turns out that the equality holds not only in that regime. So there's one other regime where it holds, because you could say the linear response regime is not that interesting. I'm not very far from equilibrium. Neither I have a large current, neither I have a large entropy production. This can hardly be a very general thing. But we'll see that this equality actually holds in another case, which is also interesting. Okay, and then of course the generating function satisfies this symmetry, which is called the fluctuation, which is related to the fluctuation theorem, which I will mention briefly. But here's another model, very briefly, where which is also very well used in the literature. I have two states, and two types of transitions can occur between those very two states. One which is fueled by a reservoir at some temperature, beta H, and another that's fueled by another reservoir at some temperature, beta C. Okay. I can, of course, write a master equation. I can find the steady state in this particular way. In here, I can do everything. I can exponentiate this 2 by 2 matrix and get anything. In fact, I can get the generating function for any initial state, not just the steady state here. The symmetry holds. And here you can immediately see it's a minimal heat engine model, because you can immediately see that the entropy production rate then is related to this beta H. Yeah, so it's sort of like the Q by T, Q1 by T1 plus Q2 by T2 that you see in your text. Okay, so this was just this, but talking of fluctuation theorems and so on. In the stochastic thermodynamics, so the results, this is among the most famous results that, if you define a total entropy production, then this holds. Okay, and of course, before that was also, this was known. If I have a current which is not the delta S total, then this could also satisfy something like this, but for large tau. But this holds actually for any tau. Okay? So a natural question, the reason I'm showing you this is a natural question to ask is the thermodynamic uncertainty relation related to the fluctuation theorem in any way? I mean, is it new information? Maybe it was all here, but we'll see that it is indeed new information, that the fluctuation theorem doesn't fully determine the relation. So, okay. No, so maybe I'll just, you can do the same thing if you have Langevin equations. You can define entropy production, trajectory wise, etc. But let's carry on a bit since time is getting on. And so what have we said? So this particular identity, I mean, inequality that I showed, it holds for steady state overdamped Langevin or discrete state space systems, time independent drives. So some kind of drive that's time independent. If there's any time dependencies of any sort, then that at least that is out of the game, but there are others. And current type observables. Because you can have other kinds of observables which are also sums, which are also, for example, what is the total number of transitions that took place or something like that. That's called activity, yes? That particular bound doesn't work, but there are other bounds. Yeah, so that's where all this interest has come in. So since that particular relation doesn't apply in all these cases, there's been an enormous amount of work in getting other bounds in all these different cases. So, okay, why does it hold? Okay, there is some, maybe some intuition. I don't know how good it is. Maybe it's not very good intuition, I don't know. So one is that, for example, that, okay, so jump processes have a lot of noise. Things are going back and forth, but there are two kinds of noise, you could say. A lot of back and forth hopping or randomness in hopping times. And you could reduce back and forth hopping by making the motion more directed, but then there is a cost. Okay, so there is some sort of balance between the cost and how directed you want to make it. Directed would just mean that you are reducing variance. So maybe reducing the variance is a good thing. That's what you want, but then you pay a cost for that. So that is one way of thinking about it. Another is that it's some generalization of the fluctuation dissipation relation in some way. But okay, so I don't have more to say about that. But again, there's work done on the relations on that. But I want to go a bit ahead and talk a little bit about what comes in the proof. So as I said, a proof which is using these large deviation techniques. And I think they were earlier developed by this old paper by Mays. And if someone can tell me how that is pronounced, that Netoshny, yes. So that's a very famous paper. And I think there were some results of that were used in this proof. The proof is to show that the generating function is always bounded by the parabola. And here, for example, again, a figure from Patrick's thesis, and that's, there's a whole bunch of generating functions here in different colors. The parabolic bound is right at the bottom here. And the ones that are closest to it are the ones that are in the sort of very linear response regime, not very far from equilibrium, but there you can see that they can go arbitrarily far from equilibrium. This bound seems to work. There are other proofs that have come since then. The interesting thing is that it's a linear, a bound that is exact in the linear response regime holds arbitrarily far away from equilibrium. So it's interesting. The proof, I'm not going through the details of the proof, but the way that the proof works is to the extent that I have understood it, is that so what they say is that, okay, so I have a Markov process. There are jumps on all these bonds. Imagine a network, and there are bonds, A, B, C, etc. And there are jumps between all these different nodes. You can think of all of them as a bunch of independent Poisson processes. Okay, but with a constraint, because it's steady state. All those sums have to add up to 0. So if you write a consistent generating function that takes care of that, then you get a sort of large deviation estimate. Okay, now I might be simplifying this over much, and yeah, and of course there are experts here who know this better than I do. Okay, so So as I said, it's very normal to ask, is this related to the fluctuation theorem? And the answer is, it is, but only for short times. So why? Because for short times, you can show that if this relation holds, so some current and this delta S total together satisfy this, then you can show that the generating function is greater than this quantity, which is what you would get for small times from log of this thing would be that at short times. Okay, so at short times it seems to work, but for for large times it's non-trivial. Okay, so at least it's new. It's something new. It's not complete. Doesn't follow from fluctuation. Okay. Yes. And for arbitrary times, if you insist on only getting a bound which the fluctuation theorem gives, it gives a much weaker bound than the thermodynamic uncertainty relation. And that has been done in this paper by Hasegawa. And as I said, there's a whole slew of results now for these underdamped diffusive, do bounds work or not, discrete time independent driving, blah, blah, blah. So there's a lot of different stuff, and this is not even mentioning everything. For underdamped diffusive processes, as I said, there is some, I don't think the situation is known, and because like very recently, I think just a few months back, there was a paper by Patrick Piazzonka who came up with a model that completely violates this bound. So I don't think anyone fully understands what's going on there, but of course it's perhaps just that just dissipation doesn't bound it. Maybe you need dissipation and some other quantity like total number of transitions or activity or something for underdamped systems for some reason. Don't know. Okay. Why is there so much interest in this whole thing? As I said, it helps you infer this entropy production. Now, of course, you might say, why do I want to know entropy production? Well, it's the first thing to know about a non-equilibrium system. It gives you bounds on efficiency, etc. So it's interesting from that point of view. It may not be the only thing you want to know, but it's interesting. What this says is that if I have a function like this, okay, if I measure something like this in my experimental data, let's just talk about experimental data of systems which I have no idea about. I measure something like this in the experimental data. I maximize it in every possible way by multiplying this current by my weight factor, whatever I want. I maximize it. I mean, I'm guaranteed that the best value I get would be the best bound for sigma, which is very nice. Then you could say, oh, I mean, isn't it hard to maximize that thing? But there are, these different kinds of algorithms which do that. I mentioned that there was something happening at short times, and so that is related to our result, and this is the only thing I have to say about it. And in that we can show actually that the inequality becomes an equality, not just in the linear response regime, but also at short times. Okay, and that sort of, I guess, Safe et al. Kind of had that result already, except they didn't quite see it this way because they had shown that it follows from the fluctuation theorem at short times. The thermodynamic uncertainty relation follows from the fluctuation theorem. So basically, yes. And so if it's so at short times, if we consider either this objective function or this one is for diffusive processes. This one is for discrete state systems. Of course, this would work also for discrete state space systems. But for discrete state space systems at short times, the equality doesn't hold. So we have overdamped Langevin equations. You have this objective function or this objective function. We calculate it on the data. I mean, so we take the data, calculate that, maximize it, and then you get a best possible value for this entropy production. And Biswajit, for example, has done a lot of experiments where we actually, at least for very simple systems, when you know what the answer should be, see that you can actually get it. Again, maximizing this is not is something that there are many algorithms for, some kind of steepest descent kind of algorithms or using neural nets or whatever. Okay, so I guess I'm done, right? My time's over. okay, so there was one more thing I wanted to say. You could also ask, if I get a best possible bound, how do I know that is entropy production? Like so how do I know that the best possible bound in fact is the entropy production? That you can actually, also there are proofs for. You have proofs for at large times and at very short times. But in between, you don't know. You might get something else. Some other current in your system could be the best possible bound. So, yes. And yes, with that, I'll say thank you.
Okay, questions, comments? Yeah, Robert.
Okay, I have one question about, I mean, people always say that, proving this inequality is very difficult and, it's a non-transparent proof. And I also look myself at some of these things and sort of share them. And now recently I heard a talk by somebody called Deepak, and, he claims that at least for the Langevin case, I mean, he has sort of a very simple proof of the uncertainty relation. Could you just comment, I mean, on
By whom? By whom did you say?
Somebody called Deepak. I mean, it's a person at two team. I think they're in Berlin or so. DIEBALL. No, okay, maybe you didn't hear. So maybe then the question is just sort of, I mean, could you comment a little bit on how difficult the proofs are? I mean,
so I think okay. So I think the proof is actually, yeah. So it's I think the idea is somewhat what I said, that at large times, I mean, if you assume all your transitions are sort of independent Poisson processes, but with an added constraint. So I at least to the extent that I understood it, this was a general idea. But then now implementing it in the system in the context of this what's called 2.5 large deviation theory is, I think, a much harder thing to do. But maybe you have something to say? Or you know the details of the proof, yeah. But I think, but that, I mean, the idea, I think, is this is what the idea is, and I think the people who proved it, like
2.5 looks a little bit high to me.
No, I think the large, it's just a combined large deviation theory for densities and currents. Yeah, that's it.
Any other question, Abhishek?
No, so I didn't quite understand this. So here you said earlier that in the linear response regime, it's you get the equality, right?
Yeah.
But here you sort of extremize something with respect to what? I mean,
so exactly with respect to what? It's respect to this. So remember this J here. What was that? I measured it on the data. Let's go back to this time series. So suppose that somebody gave me some data. I didn't know anything. I could identify A, C, and B, but I didn't know WAC and WBC. I didn't know anything. Okay. But I can, of course, I identify these states. So I can keep track of how many jumps there are between. At the smallest resolution that my experiment can give me, I can keep track of how many jumps there are between states. I can multiply it by this weight factor, DBC. That is what I maximize it over. That's the only variable. I mean, that's the only thing I can vary in my system, right? Given the data, nothing else. Then I'm guaranteed, both at the short time and in fact at the large time too, that this DBC will be exactly this FBC, this quantity, log of the ratio of the rates, if I maximize it. But at large times, it's still only a bound. At short times, it's equal. But of course, you have to keep track of the fact that, I mean, maybe you missed some states or something like that. I mean, so the equality will only strictly hold if I have a fantastic, I mean, like perfect experiment where I keep track of all the relevant states of my system. If I had hidden variables or if I had coarse graining of some sort, then no matter what I do, I'll only get this inequality. But it will still give me a bound. It will still give me a bound. So to answer your question, I mean, this is the thing you.
So these DBCs are just something you put by hand, not
it's
not in the rates or anything.
No,
right?
you put by hands and then you just optimize it.
But it could be like some hidden variables which
that you don't know about. Then okay. Then of course, then whatever you do, the best you will get is a bound. You never get the exact one.
Are there other questions? Supriya, can I just ask
Of
one
course,
question?
of course.
What is the, do you have any simple sort of intuition for this factor 2 on the right? Is there any simple reason for that?
The factor 2, okay, let me think. Okay. In fact, I can tell you when tau is very small. Then then, as I said, the fluctuation theorem somehow imposes this. Okay. So what it tells you is that this entropy distribution is a variable where the variance is equal to twice the mean. I mean, so for a Poisson process, variance equal to mean. But for this, if the fluctuation theorem has to hold, then the variance has to be twice the mean. At least, yeah, in the short time. So it's a Gaussian. Yeah. Something like that, yes.
Right. So
Yeah, sorry.
Yeah.
So you seem to say that given a time series, you can calculate this and maximize the variance or some such thing.
Yeah.
But actually, you are averaging over all possible time series when you define the variance, right? If I take a single time series, then for the end-to-end current difference, there is only one realization and the variance is 0.
No, so what are we doing in, suppose we had a very, very long time series, then I'm chopping it up into time series of length tau. And then for each of those lengths tau, I compute a mean and a variance, I mean, and a value for this G square.
No, but
Assuming there's none.
suppose I'm contrary and I want to consider the whole sample as a single tau, then there will be no variance in the answer because I'll calculate.
So then I have to do different experiments or what?
No, so you are doing an average over an ensemble of time series. It's not really defined for a single time series.
Yeah, so if you want to get a good value, then yes, you need to get but
Okay.
I mean, I think that is correct, yes. Correct.
if there are no other questions, thanks Supriya again.
Thank you.